Hello, this is Jason Kendall. Welcome to the next of my introductory, or not really so introductory, astronomy lectures. Today we're going to dive deep into special relativity and show people why that traveling faster than light isn't possible. Or more specifically, wishing don't make it so. So let's see why traveling faster than light, though it's magical to think about, isn't actually possible. Faster than light speed travel is the staple of television and science fiction and movies on the interwebs and so forth. And everybody's coming up with some wild idea about how to go faster than the speed of light. And in, in television shows, they just say you do some crazy engineering trick and all of a sudden you're going faster than the speed of light. You tweak this knob or dial this dial or plug this box into there. And if you build the right thingamadoodle and you plug the woozle compactorator into the hamtronicle and it tram-tiddles the tagaloo and voila, you're going faster than the speed of light. So faster than light travel, or FTL, is a staple of science fiction. But can it actually be done? And the answer is no. Too bad. Unfortunately for the future purveyors of fine hamtronicles, no one is going to go faster than the speed of light. Why? Well, there's two major rules. The first, which we'll discuss in some detail, are the rules of special relativity. And two, I'm just going to leave this really important thing out there. It's called the principle of causality. And the reason we do that, in television, we don't necessarily think about these things, and shows, they don't really care about it. But because it makes time travel television much better and shows better, because then you don't have this thing called causality and you don't have to worry about it. There are a lot of things wrong with that, but really, causality is something we do have to discuss. So it's this thing called reality, and special relativity, just before I begin, has been extraordinarily well tested, well understood. It's so incredibly in part of physics today that in fact the International Bureau of Standards in Paris doesn't even define the speed of light anymore. It's they define the speed of light to be what we used to be measured, and they use that definition to define either the second or the meter. And so those are the things that speed of light is done, and because of the trust that we have in special relativity. Let's go take a look at this thing called reality. The first of the two rules of special relativity. One, the laws of physics for all uniformly moving observers, no matter what the observer is doing, are all the same. Uniformly always means with a constant velocity. That means there's no acceleration, no rotation, no curves and twists to the motion. Either you're standing still or you're moving uniformly, meaning with a constant speed in one direction and not changing speed or direction or rotation while you're doing that. Basically, if you're standing still to somebody who's walking by you, then you seem to be moving to the person that's walking by you. Now, the laws of physics, therefore, all of the laws of physics are the same for everyone if they're moving uniformly. It doesn't matter how they're moving, so long as they're moving with a straight velocity. And this is one of the first of two great principles of special relativity, and it implies that there's no such thing as absolute rest. Somebody is always moving with respect to somebody else. That's what we mean by no absolute rest. There's no, apologies to the Buddha, who is at the center of all creation, sitting and minding his mantras. But the idea is that there is no one place that is purely at rest, where everything else is moving with respect to it. It doesn't exist. So there's no such thing as an absolute speed. There's only relative speeds. And any uniformly moving observer can consider themselves to be at rest. If you're moving straight in a line, then you can be considered at rest, which is really interesting. Well, why? Well, think about it. I'll give you a chance to think about it. When you're on a subway platform and you're going on the subway, sure, there's some bounces, but if it's a smooth ride, you're moving 60 miles an hour or whatever it is. Maybe it's really fast. Or if you're on an Acela between Boston and New York and you're on a straight track of road, you're moving 80 miles an hour. Or if you're in a plane, you're moving 400 miles an hour. Those things can all be seen to be at rest. You're not accelerating or decelerating. You're not turning. You're not twisting. And so everybody sees their own reference frame in every one of these things as normal. All of these things are seen as normal inside of an inertial reference frame. However, it's different for people looking at you. So every possible physical experiment that you might do, any measurement of distance, length, and time and things thereof, will be the same, no matter what your speed is of your frame of reference. The next thing we're going to do is we can say, well, we're going to look at the second principle, and the second principle says that the speed of light in a vacuum is the same for all observers, regardless of their motion relative to the source of light. That's kind of a weird one if you think about it, and we're going to look at that in some detail in a short bit, but keep in mind that no matter how you're moving, no matter how anyone is moving with respect to you, no matter where the source of the light is, all people will always measure the speed of light to be the same, always. That's kind of what we said before, but this is different. So the speed of light, therefore, is a universal constant. It is a constant that applies to everything. So we can't send messages faster than the speed of light, and we could talk about why. Well, there's a funny thing you could say that we can't send them slower either, but that's a funny part. But the most important thing is that this concept that the speed of light in a vacuum is the same for everyone has been experimentally verified in many, many cases, and the speed of light does not add or subtract to the relative motion of the observer or the emitter, which is really interesting. So those are their two core principles of relativity. We'll see how they affect later, but let's go talk about the most important one for our time travel thing, which is the principle of causality. Principle of causality simply means that anything that is an effect must be preceded by its cause. If I'm buttering some bread, and I'm at home buttering some bread, and I'm making Texas toast, right? And I'm going to grill that Texas toast on my grill. So what I do is I put the butter on the bread, and as I turn around to put it on my grill, I accidentally drop the bread, and of course, because it'll land butter side down. Why did it land butter side down? It's because I dropped it. So it doesn't just magically be on the floor by itself without somebody dropping it. Either somebody dropped it, or threw it, or pushed it there. It just doesn't appear there, and then all of a sudden is in my hand. Like, oh wow, there it was on the floor, now it's in my hand. No, we have a sense of causes and effects, and everything that must happen, that every effect must have a cause, and its cause and the cause that causes an effect must be before the effect. It's an interesting thing. I use the example below of a baseball bat. I like Texas toast just as much. Okay, so this principle of causality says if you do something and it causes something else to happen, then the thing that is caused to happen afterwards must happen afterwards. That's what we mean by causality. Measurement of length and time. So this is an important thing that we have to deal with when we talk about this, because measurements are everything. What do we mean when we say going back in time? Well, we're measuring time, of course. So now we got to understand why faster than light travel is impossible. We must understand what we mean by speed. And speed is distance through time. And that's all speed is. We're not talking about acceleration, which is the change with speed through time. We're talking about speed, which is just how fast are you going in a given direction, and how much distance do you cover in an interval of time. So with these kinds of measurements, we do that pretty well. People can measure speed very well, and we can measure things going left and right, and we will call that x. Why not? Because what the heck? So x shall be, for the purposes of this lecture, our label that we will call any distance measurement that we're going left or right. Back and forth we'll call y. Why? Because, I like you. So y is the left, is the back and forth measurement, and the up and down measurement is z or z for those out in London. And the distance measurement, all these things are distance measurements. You can go either way with distance, but with time, we're watching a clock tick, and clocks tick one tick after the other. So a time measurement is the total number of ticks that we see in a series of intervals that go tick, 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 where the intervals are regular for whatever reason that they are regular. And so what we have then is we are going to put all of these distance measurements and all of these clocks in a funny thing that we call an inertial reference frame. An inertial reference frame can be thought of very interestingly as a series of, almost like a jungle gym or a grid or a cube, a series of cubes or grids of rods that are all connected at the ends. They're going either backwards or forwards, up or down, or left and right, and they're going X, Y, or Z directions. And at the intersection of all these rods, as they intersect at a vertex, they will have a clock. And so we've got these, maybe they're 1 meter long rods, and they're going left and right. You have a clock, and there's a rod going left and a rod going right, 1 meter long. And then maybe you have another rod going up at 1 meter and down 1 meter. And maybe you have another rod going forward a meter and back a meter. And so each of these things are at 90 degrees to each other. And we can think of this as kind of a big, big plus sign or what have you. But that is a piece of our inertial reference frame. Now take a gazillion of these and put clocks on the ends of each of those rods and stick them all together in a big, 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 big lattice. And what do you get? You get what's called an inertial reference frame. You can measure distances inside this frame, and you can measure times inside this frame. All of the clocks in an inertial reference frame are synchronized together, and all of the rods are the same length between the clocks. And that's our frame. So why do we want to bother doing that? Because we want to show how frames move with respect to each other, and that's what we call Galilean relativity. So Galilean relativity is because we're hunting for causality problems. We need to see how things move with respect to each other. So we're going to keep this really simple, and we're going to introduce the letter V for velocity. But we could just use the word SV for speed because we're not going to change velocity. Velocity implies direction, but this velocity is only in the x direction, which is forward and backward, right? Which is left and right, according to us on this grid. Remember, y is back and forth and z is up and down. So we don't care about up and down motion or back and forth motion. We only care about left and right motion. If somebody's zooming by you at speed v, then that is how you will say, oh, how fast are they going by me? They are going 60 miles an hour, and in 1 hour they will travel 60 miles to my right. That's what that means. That's what that v is. And that's what we mean by the x value. And that's what x minus vt means. It's like, oh, what's your starting location? How far will you go in a given period of time? We want to actually translate between two reference frames. That's how we're going to find our causality violation that gives us the thing that says that time travel can't happen. So stick with me. So let's actually see what this funny set of equations on the left-hand side really means. We have a series of things that we'll call unprimed land. So we have our t, x, y, and z in unprimed land, and we're going to postulate that we're outside a moving car. And the moving car is moving straight on a very straight highway going to the right, as it seems from this particular thing. And we're watching that car go to the right, and it shall move with speed or velocity v, and how far it goes will be v times the time that you watch it go. X minus vt, x is the direction, that is the right-hand direction. Y is the place, x is where you measure it to be, y is where you measure it to be, and z is where you measure it to be. Since z is kind of like going up or down a hill, we're not going up or down a hill, so it's going to stay at 0. It's not going to change. Y is going back and forth. Since it's a straight road, it's not going to change either. T will also change. It will tick. The clocks will tick. Now, Galileo said that everybody's clock is the same. That's what Galileo said. So you'll notice that the time is the same, these two equations there. But the distance, let's say somebody's going by you, they are going to move to your right as you watch them go by. And so specifically, if you want to look at if we want to look inside the car, not just the car itself, but all the contents of the car. And in particular, let's look at a car's coffee cup holder and a coffee cup inside the coffee cup holder next to the driver of the car. As you see, the car has a coffee cup in it. The coffee cup can be thought of as moving by you at 60 miles an hour. Now, if the car were completely invisible and everything were invisible, then you just see a coffee cup moving by you at 60 miles an hour. You'd wonder what's going on, and you'd wonder if there was an invisible car. And maybe you would. That would be very interesting, too. So there is an invisible coffee cup moving to the right. Well, it's visible too because you're looking inside a transparent car, seeing the visible coffee cup inside a transparent car, or semi-transparent, because there's a guy driving in there, or a woman, and maybe he or she, or maybe they're going on a date when they're a transparent car, and they're taking coffee with them. And so the coffee cup and the man and the woman are in the car. They're driving to the right, and it's a very strange looking thing, as two people seem to be in air with a coffee cup between them, and they're driving down the road. Okay, so the car, that is their speed, whatever it is, maybe 60 miles an hour. Now, what is it like inside the car? And that is the primed location. Remember, to them, it is at rest. They are at rest inside the car. The coffee cup is at rest inside the car. everything is at rest inside the car. They're moving with respect to the outside world, but inside the car, they're all at rest. Nothing's happening, nothing's falling down, nothing's rocketing around inside the car. They don't have the kids with them, so nobody's throwing stuff from the back seat. The car itself may be moving, and that is the reference frame, is the car. Maybe the car is attached to this big reference frame and it's dragging it with it or something, but it's all threaded throughout the car. So the car is now the reference frame. Maybe they've painted the inside with all sorts of little clocks, and they're kind of boxing themselves in with that lattice of wire rods and things, just to make sure that they can measure that nothing's actually moving, including themselves. Prime land we'll call inside the car a moving cabin. Nothing inside the car is moving. The car itself and all the contents and everybody in it is moving to the right very fast, according to us on the outside. And as they look outside to us, they'll see us going the other direction, backwards. So notice that it's symmetric. If you're in the car, you feel at rest, but outside the car appears to be whizzing by. That's the essence of Galilean relativity. But everybody's clocks are the same. Everybody's clocks are the same, which means that in addition to that, let's say Galilean relativity, it means that speeds then add together. And this is where we're going to get onto the whole faster than light thing. Watch out. So now we're in this car. I'm in a car driving 100 kilometers per hour. Hey, metrics, right? So 100 kilometers per hour, which is 62 miles per hour, by the way. And you're on your way to internet fame by shooting a gun forward out of the moving car. And of course, the bullet is going really fast, 1,000 kilometers per hour or 600 miles per hour, which is a pretty fast bullet. And then some diligent observer from the Hold My Beer Institute measures the bullet, of course, going 1,100 kilometers per hour. The car's speed is added to the bullet's speed because the bullet started from rest at 100 kilometers per hour with respect to the car. If the bullet goes forward at 1,000 kilometers per hour, irrespective of wind resistance, right? And we just get rid of the wind. For fun and enjoyment, get rid of the wind so it doesn't slow down. It'll simply add on. So Hold My Beer Institute is doing this great experiment, and they find that they measure the speed of the bullet using a local police officer's held beer speedometer or radar gun. And so what they find is that the actual speed of the bullet is going faster than it would otherwise because it's being shot out of a moving car forward. So now let's try instead, the Hold My Beer Institute gives you a laser in the car, and you can do the same exact thing. If you're driving the car and you hold the laser out the window and you shoot it forward, how fast is the laser going? Now, if your car is going 10,000 kilometers per second, very fast car, very, very fast car. But if your car is going 10,000 kilometers per second, you shoot a laser beam forward, which the laser is going 300,000, because it's light, it's going 300,000 kilometers per second. No one measures the laser going 3,100 kilometers per second. It does not get measured that way. The guy with the clipboard from HMBI measures it to be going 300,000 kilometers per second. You in the car also measure it to be going 300,000 kilometers per second. If you somehow manage to get your car up to, say, 299,999 kilometers per second and shot that laser forward, the laser still would be going only 300,000 kilometers per second with respect to you in the car and with respect to the clipboard guy. Both of you would see that. Light only goes the speed of light for all observers. That is the essence of special relativity. And if you don't think that's weird and you don't think that's very strange and why that's a central postulate to special relativity, then pause the video and think about it. Okay, you've done pausing. Now come back. So that means that we no longer have Galilean relativity. No two observers, therefore, moving with respect to each other. They both experience the world quite differently. Both measure the same speed of light. Both find and use the same exact physical laws, measuring distance, time, mass, energy, everything. But in applying those laws, they measure different distances, times, masses, and so forth. And both of them are correct. Which one's correct? Both are correct. I'm going to say that one more time. Who's correct? Both are correct, because this is what we know as, this is called special relativity. Relativity means the measurements that you make are correct for your reference frame. And they are translated. So you can translate your measurements into another measurement of the reference frame's measurements. And then there is a way to do that. And we'll discuss that very shortly. So now here's a trick, because everyone sees C. See the rocket, the spaceship is flying by, and they say, I go 0.1 C, or 1/10 the speed of light. So the beam is going forward, so they see C. And this beam of light is always going to if it's going to the right, the rocket's going to the right. No matter how fast it's going, everyone sees C. And C is given by this is the common way we talking about the speed of light. You'll see that through all of physics. And below is its exact value, 299,792.458 kilometers per second. That's actually the definition of the speed of light, because special relativity is so well trusted and so well experimentally verified that this number is defined to be the speed of light, because the speed of light is a universal constant. Everyone sees it, so it is a definition. All right, so Einstein then came along in 1905 and reconfigured Galilean relativity and said, wait. If the two postulates of special relativity are correct, then we cannot use Galileo's configuration for the translation of going from one reference frame on the side of the road into the car anymore. We must therefore, because you would add speeds, because Galileo's relativity says we would simply add the speeds, but that is not true. That is not true in special relativity. In fact, it is experimentally verified to be not true, so we cannot use Galileo's way of transforming from one reference frame to another and measuring clocks and differences between them. How do we get between them? How do we compare our measurements from outside the car to inside the car as it's zooming by? How do we compare them? And we use these these four equations that translate the time and distance measurements. Notice under Einstein's configuration, we have the measurement of time, meaning outside the car, to be t, x, y, and z, which are the unprimed things outside the car. And we have all these funny things. We have c, we got the velocity. We've got now a gamma, which kind of looks like a crazy little y, which is the inverse square root of the difference from one of the squares of the velocity or speed at which they're traveling compared to the speed of light. So that gamma is a really interesting thing that shows the limitation between the two. But inside the car, again, remember, it's just the prime land, which is just what you're measuring. Prime land is inside the moving reference frame. And you want to translate your measurements outside of your reference frame into the measurements of somebody else inside the other reference frame. That's why the minus was there in the Galileo's group. It's not that it's how fast they're going. We're trying to translate from one reference frame to the other because we want to compare the two reference frames. We want to compare ours to theirs. We want to know how they compare. It's this translation group that tells us how they compare. And notice the time now has a bunch of very complicated looking things associated with it. It's no longer just the times are equal. We no longer have that. The time measurement that we do on the ground is different than the time that we see if we look at a car going by. The clocks are no longer in sync. And in fact, they read very different numbers. Your gamma there is always going to be some number that will be, if it's going to be, the closer it gets, the V gets to C, meaning approaches C, then that number approaches 1 in the big gamma thing. And if it approaches 1, then the difference is really small. And the inverse of a very small number is a very large number. So the faster it's going, the slower the time appears to be going in the moving reference frame according to us outside. So everyone sees the speed of light the same, and it also leads us to a new conserved quantity. And that quantity is very important to note, and that's what that little equation down in the lower right is all about. And the little equation way down in the lower right is the following thing. there is an invariability now of the space-time interval. The space-time interval is invariant for all observers in special relativity. Notice that we have our dt squared, our dx squared, dy squared, and dz squared. Now, what do these d's mean? And what these d's mean is little bit of distance. So a tiny change in x, y, or z, or a tiny change in the time, and we add those things up, and notice that there's a really strange thing about the dt, is that it's multiplied by the speed of light, right? And both of those things are squared, and it's got a minus sign in front of it. So if we take the distance that is changed in x in our frame, and the change in time in our frame, multiply that by the speed of light, and difference those two things, and then we look at ds, which is now what we call the space-time interval. And that's the thing that doesn't change. Now, inside one reference frame, the ds is one thing, and outside, in the other reference frame that's moving by it, the ds is the same. The ds squared is the same. So both observers see the same space-time interval. And this is because they can translate between the two reference frames using the four equations below, with the gamma being kind of defined off to the side just for things. And those four reference frames are called those four translations are called the Lorentz transformation. And we're literally saying, hey, I'm measuring my time and space over here, and I'm seeing somebody zip by. What do their clocks look like? What do their measurements look like? And how can I translate from there to there? So the space-time interval is the thing that measures between them. And in fact, that you can actually take the two sets of things and sum them up in this way, and the things fall out as an equivalence. I invite you to actually plug the gammas in and see if this actually works with respect to this ds squared. The space-time, or is it called space-time? So that's the important thing. Before Einstein came along, the concept is that space and time were separate things. The universal clocks ticking everywhere, a God clock that started now and goes on. And that was Galileo's idea. That was Newton's idea. That's what they operated under. But we find instead that because the speed of light must be a constant for all observers, then we have to mix space and time. And so when we talk about space-time, this is why. So we don't measure it, say, in left, right, backwards, and forwards, just that. We measure it left, right, backwards, and forwards and subtract from it the time interval squared times the speed of light squared. And that total summation, 3 positives and 1 negative, gives you the space-time interval through which an event occurs, or the distance between two events, or just where something is in space and time. And that's the important thing. And that's why we call it space-time, is because the space-time interval, ds squared, is the new invariant. So Newton's laws said that they were separate, they were absolute. Galileo thought that. Newton realized there was something a little wacky about that, but he didn't have the energy or there was not the knowledge for him to actually pursue it. But eventually Einstein came along and found, yes, they're together, and this is all a result of the results of Maxwell's equations, or Maxwell's formulation of electromagnetism. The Maxwell's electromagnetism showed that there must be something strange about the speed of light. And if you go look at my video on the Michelson-Morley experiment, you will learn more about that. We now know that the true way of talking about distance in space and time is to mix them together using this ds squared, or the space-time interval. And that's how we measure distances in space and time. That's what it's always about. In sum, everyone sees C. No matter how you're moving or where you're moving or how you're oriented, everyone moving uniformly always measures the speed of light being the same. The speed of light is a constant for all observers, no matter how they're moving with respect to the source or if they are the source. So let's take an advantage of that to look at a couple examples. First, let's create a bouncy light clock. So we have a box that's 1.5 meters high, and we got a laser that shoots a laser off a mirror and bounces it off and gets to a detector. Because it's the path is exactly 3 meters, it makes a little bit of a nice math. It makes it basically nanometers is what we're talking about. Nanoseconds is what we're really talking here. So we can think of this as a clock, meaning the laser shoots pulses at regular intervals, and the detector tells the time by listening for those pulses. And that's what we care about, is the pulses that come from the laser and the detector. and the laser's just doing its thing, and the detector's doing its thing and detecting them. So the pulses occur, the detector detects, and as it detects them, that is just the same as a ticking clock. What we find then, because of special relativity, is that time dilation shows that moving clocks run slower. Why? All right, so now let's take our bouncy light clock and put it on a rocket and launch it. And now it's going really, 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 really fast. Maybe 80% the speed of light. That's a really fast rocket. Yeah, we got some money from it. We got a big boost of money from Congress. They got over themselves and decided to fund our near light speed attempt to go to Alpha Centauri with our friends so that we can have Alpha Centauri cake, because they hear that there's a really good review of it on Yelp. On the rocket, while we're traveling to Alpha Centauri to get that really great cake, we're taking time measurements to see how long it takes. And our clock is this bouncy light mirror thing. That's what's doing it. That's our clock. Now, let's say there's somebody on the moon watching us go by, or on Pluto, or halfway out between there that just got stranded, so they were just watching us go by. As they watch us go by at 80% the speed of light, they see the laser move out from the pulses move out of the laser beam, out of the source, bounce off the clock, and get to the detector. Notice, because it's moving to the right at 80% the speed of light, that the actual path length that it takes is longer than if it were standing still. So, measured on the rocket, we see a 3-meter path. Measured by someone watching it go by, it's a much longer than 3-meter path. Maybe 5 meters is what we have. And that's why I chose 0.8c, because, hey, that makes it a lot easier for the math. But both are correct. Why? The rocket speed, on the rocket, how fast is the rocket going? A constant speed of 0. Inside the rocket, nothing's moving. Everything's still. Everything's stationary. The reference frame of the rocket is fully stationary. But on the ground, or in space, watching it go by, it's moving by at 0.8 the speed of light, 80% or 0.8 the c. That's really fast. Now, the photon speed, the photons that are leaving the laser and going to the detector, are moving at the speed of light c. No matter what you do, that's what everyone sees. Everyone sees c. So inside the rocket, the photon's path length that it goes is 3 meters. Watching it from the ground or from space, the path length we see is 5 meters. And so therefore, one tick of the clock on the rocket is just 10 nanoseconds. However, on the ground, it is actually 16 nanoseconds, which is really interesting. So on the ground, away from it, watching it go by, we see that actually the ticks take longer because the path length is longer. So therefore, time must be slowing down. Therefore, there's no absolute time, and everything's affected by this. Heartbeats, movements that people see. It's not just this clock. It's everything. People's movements, speech patterns, everything. You drop something, it falls slower. Everything appears to be moving slower on the rocket as it zooms by. That's really fascinating. Also, there's another effect as well, which I'm going to use this way. When cosmic rays hit the Earth's upper atmosphere, meaning there's these particles from outer space, maybe they're coming from the sun, maybe they're coming from a distant supernova, and they impact our upper atmosphere, what happens is that they hit the Earth's atmosphere at very high speeds, extraordinarily high speeds. They create numbers of particles in a cascading shower, and some of the particles that are created, the particles are like protons and helium nuclei or electrons. That's what's hitting the atmosphere. And, they're packing a punch. But when they hit the nitrogen, or they hit the nitrogen molecules, or the oxygen molecules, or the ozone or something, and they hit something in the atmosphere, they create a cascading shower of subatomic particles, and some of them are called muons. And a muon will decay rather rapidly as it goes. And it'll last only a few milliseconds, a few microseconds before it decays. And a muon will become, I believe, an electron or something else, and some other stuff. What's fascinating is that these things are created very high in the Earth's atmosphere, and as a result, they're also byproducts of decays of other things, so they get created very high up. So what will happen is that they have a very short lifespan, and the cosmic rays themselves hit the Earth's atmosphere, and then they live for this short period of time and decay. But the height of the Earth's atmosphere and the speed with which they're known to traverse the Earth's atmosphere shows that they shouldn't make it to the ground. It's like saying, hey, I want to travel 100 miles in 1 hour, and I want to only go 10 miles an hour. Everybody looks at you and shakes their head and says, you got to go 100 miles an hour if you want to make 100 miles in 1 hour. He says, no, I want to get there in 10 by only going 10 because I'm scared of going fast. People would shake their head at you. But muons their lifespan is very short. And if the distance from the top of the Earth's atmosphere, where they are formed, to the bottom, if you're traveling at normal speeds or even very, very high speeds, is too far a distance for them to traverse, such that they can make it to the ground at all. Well, that's what's interesting. From the muon's point of view, what happens, which is really interesting, the muon sees something different. Well, we see that the muon itself lives longer because it's moving faster. Now, what does the muon see? The muon just lives, remember, it sees its own reference frame. Everything is normal. So how can it then live for that length just because we see its clock going slower? The flip side is that the muon sees the atmosphere as shorter. So there is a length contraction in the direction of motion. And from the muon's perspective, remember, it's at rest and it's traversing something. The speed with which it's traveling through the Earth's atmosphere means the Earth appears to be rushing at the muon. The muon's not moving. I'm just a muon. I'm hanging out. I'm at rest in my reference frame. I don't care how fast you think I'm going. I'm at rest. And the muon is flying down through, so the Earth's atmosphere is contracted as a result of its motion. Or more specifically, it looks like the Earth is rushing towards it. So what the muon sees is the Earth's clocks are ticking slowly, and the atmosphere is foreshortened, and everything is smaller in the direction of motion. So therefore, we have this funny thing. In the laboratory reference frame, meaning watching it fall, we see it get created maybe at the top of the mountain, and the mountain appears a normal height to us, but if it were created at the top of the mountain, it wouldn't make it to the bottom of the mountain because it lives too short a period of time. So therefore, it has time dilation. We see its clock running slowly due to the Lorentz transformation and the constancy of the speed of light and the space-time invariant interval. We measure its clock running slowly, and that's why it can get from the top of the mountain to the floor, to the ground. However, the muon, inside the muon's reference frame, the clock is running normally. So the only way that can happen, both things can happen, is if, according to the muon, the atmosphere is foreshortened because the Earth appears to be rushing at it. That is interesting, and it's called length contraction. So the muon sees length contraction. It would also see our clocks running slowly, but for this purpose, the most important thing is length contraction, and we see its clock running slowly, and muons basically have no size, so we really can't tell if it's having length contraction. That's really interesting. And in fact, what I've just described is something that is actually observed and is one of the tests of special relativity. So the consequences of special relativity are the following. All observers that move relative respect to each other, they do not measure the same times. If you're moving with respect to me, I see your clock differently, and it's symmetric. You see my clock running slowly. Both measurements are correct. They disagree, therefore, on what things happen at the same time. You do not measure the same lengths, you do not measure the same masses, and therefore, another important thing which we won't discover here, but you can go look at my other videos on special relativity, you'll find that this is a reason why mass and energy are equivalent, and therefore, anything that has no mass moves at the speed of light. So light has no mass, so therefore it moves at the speed of light, and it can only move at the speed of light in its own reference frame, which is really fascinating. So we have, these are incredibly important consequences of special relativity, and now we have the machinery in order to say, what about tachyons? Tachyons are hypothetical, totally dreamed up particles that always move faster than the speed of light. If one came near you, you wouldn't see it until it arrived. Why? Because it's moving faster than the speed of light. So any communication that would come from it can't get to you until it's at you. So tachyons, if they existed, would simply appear. And then you'd see this really, really funny thing as one piece of it is receding away from you, and another piece is going the other direction. So from wherever it came from, the direction it came from, you'd see a piece going the opposite direction, running backwards in time, and we would see something moving forwards in time as well. Actually, both pieces would appear to be moving forwards in time, but there would be the same particle apparently moving in opposite directions. And so there's that kind of crazy diagram. It's a very tricky thing to talk about, but let's just give it that's why I give this kind of tadpole-y sort of diagram. Please go look it up on the Wikipedia. It's a nice little article. But the thing is that these things move faster than the speed of light, and the less energy they have, the faster they go. So if they're at zero energy, they would be running at infinite speed. If you want to get them slower, then you have to impart more energy into them. The more energy you give to them, the slower they go, and the slowest possible speed for a tachyon is the speed of light. So you can't actually make one stand still. There is no such thing as holding a box of tachyons. So that's another funny thing. Where are you going to get a box of tachyons from? Well, you can't find them because remember, once you've found them, the only reason you know where they're there is because there they are, and now they're with you. So tachyons move faster than the speed of light. They cannot be made to move slower than the speed of light in any reference frame. The mass of tachyon would therefore be imaginary, which is a funny way of saying the mass has the square root of -1 in front of its mass, which is a very, very strange concept. What would that even mean to have a square root -1 mass? Well, that's a tachyon. Here's the tough thing about tachyons is that they don't exist. There's no actual experimental evidence that any of these things exist. It kind of sucks. Because we could build a thing called a tachyonic anti-telephone. So a tachyonic anti-telephone is a telephone that is a very strange thing. It sends messages backwards in time. That's what an anti-telephone is, because you call up a friend, you want to say, hey, how are you? And they answer, I'm fine. And then you say, that's great, let's go to a movie. Sounds great. Which movie? I don't know. And thus begins every conversation about going to movies. So in 1907, Albert Einstein created, after he did in 1905 his special relativity, 1907 he said, how you can actually have a faster than light signal that would then violate causality. And more important than special relativity is actually this thing called causality. Causality is a core concept in physics, because you can't just have something that happens before something else unless that thing that happens before something is the thing that causes the thing to happen that comes after it. Right. This is called Tolman's paradox, in that you can create any faster than light signal will create a paradox of causality. That's the thing. So let's see what that is. No faster than light transfer. So this is not a mystery. So the point is that according to current understanding of all physics, no such faster than light transfer is possible. Tachyons don't even exist theoretically inside the standard model of particle physics. So there's no even experimental reason they exist, and there's no justification for them in any model of particle physics. But they have them in the science fiction shows, and everybody thinks time travel is possible, which it isn't. So let's talk about it. So here we go. Welcome to Fantasy Spaceland. So I got two brothers, Damon and Travis, and they want to try out their tachyon anti-Mabel device to see how it works. So this is an idea that was laid out by David Baum back in 1965, and I'm just going to play with this idea. Go check this out. So we got two brothers, Travis and Damon. They're in different rockets, and they're zipping by each other. And what they do is they have, in those little red boxes, what do they have? They've got tachyon anti-Mabel devices, and those are the red boxes with the thing in it, so they're going to communicate with the tachyon anti-Mabels. And the tachyons themselves have been calibrated, have been established to traveling at that incredibly slow speed for them of 2.4 times the speed of light. So 2.4 times the speed of light is pretty fast. That's really fast. That's faster than the speed of light. That's what tachyons do. So let's say the two ships now pass each other at going at a relative speed of 80% the speed of light, or 0.8 c. And just when they pass each other, just at that passing, when the tachyon anti-Mabels are close to each other, we'll call that the 0 point, or the starting place, or the origin. And you'll see why later. So now they pass each other and they keep going. So at 300 days after they pass each other, Damon, according to Damon's clock, at T under 300 days, he has some bad tacos. So he gets in the spaceship taco fridge and he goes in there and he gets taco. And he grabs that stuff and he gets some good things. He said, wow, it's going to be a great taco. And then he had, oh man, 300 days, that's pretty old taco meat. So he eats the taco meat and he gets a little sick and he has an event later in the afternoon. So he says, oh goodness, I ate some bad taco meat. So he's going to send that message to Travis. And the message is going to travel until it gets to Travis, according to Damon, at a speed of 2.4 times the speed of light. Now, from Damon's perspective, they're moving really fast. So it's going to take a little bit of time for the tachyons to catch up with Travis. So therefore, Travis moves a little bit further and it finally catches up to him. At 300 days, he sends this. Now, according to Damon looks, because it takes 150 days for the tachyon to travel to Travis's anti-Mabel, tachyon anti-Mabel. It takes 150 days, according to Damon, to travel 2.4 C over to Travis. That's when it arrives, according to Damon, at Travis's rocket at Damon's clock of 450 days. But Damon measures, because of special relativity, and they're moving uniformly, not accelerating or decelerating. Notice I don't have rocket engines going. They're just going and coasting at that very fast speed past each other. Because of special relativity, Damon measures Travis's clock as going slow. So therefore, the time dilation that Damon measures Travis to be means even though Damon's clock reads 450 days, Travis's clock only measures at that moment 270 days since they passed each other. That's because of the time dilation effect of special relativity that Damon sees on Travis. So Travis knows that the anti-Tachy-Mabel will do something interesting. So he says, don't eat the taco meat. So he's going to send a message back to his brother and say, don't eat that meat. And so watch what happens. So Travis's return message travels at also because it's the same machine, travels at 2.4 C starting when his clock, because that's what his clock reads. His clock reads 270 days. That's what his clock reads, 270 days. Again, time dilation is symmetric. So Travis measures Damon's clock to be running slowly. So because Travis's clock says 270 days, going back to there, Travis sends his message. Damon's clock, according to Travis, at the time he wants to send it, when his clock says 270 days, Damon's clock, according to Travis, reads 162 days. So he sends it along. And it arrives. Travis's clock then gets to Damon when Damon's clock reads 243 days. Wait, that's 57 days and Damon's passed, and so Travis now effectively warns Damon about eating the taco meat 2 months before he even eats it. That's a problem. That's a problem. That's called a causality problem. This whole thing arises because the Lorentz transformation, as we measure time and distance from moving from one frame to the other frame uniformly back and forth to each other, no matter what, and because of time dilation and the constancy of the space-time interval, we've just created a way of sending a message that Damon can send effectively a message into his own past, which is really fascinating, knowing what Travis would do. Tachyons, therefore, violate causality, and because their messages go backwards in time with respect to the reference frame that's moving according to Tachyon's source. That's really interesting. So what do we mean? Let's look at the numbers here for just a bit. So special relativity demands causality, or at least it doesn't really demand causality. Physics demands causality. That's a very important thing. Causality is just a cornerstone of our thinking, and we're not going to let that go for any reason whatsoever. None. I mean, really, we're not going to let that go. When it's measured by Travis, the message from Damon arrives at 270 days on Travis's clock as measured by Travis. Damon's clock, when Travis's clock measures 270 days, Damon's clock would read, according to Travis's measurements, 162 days. So what does he do? He sends his message across to Damon, because this is what Travis sees. He just says, oh, I get a message. Bink, it just appears at 270 days. So he sends a message, which takes some time to get to Damon. So according to Travis, Damon will get it 243 days. That's just fine. But notice it is kind of traveling backwards in time from Travis's clock to Damon's clock, between 270 to 243, which is really interesting. So that's what Travis sees. He sees the tachyon message going really fast to Damon, gets to Damon's clock at 243 days. Let's see what Damon measured. Remember, Damon sent the message at 300 when his clock said 300 days. And by his measurement, Travis's clock would have said to 180 days because of special relativity and time dilation. So when Damon's message gets there, his clock is advanced to 450 days, and Travis's clock is only advanced to 270 days because of time dilation. That's important. He started the conversation by sending the message when his clock read 300 days. Interesting. So now, Travis then sends the message when he gets it, when his clock measures 270 days, and he sends it back to Damon, and Damon's clock now measures 243 days. So therefore, it must measure when he goes back into his past, so that's why it's in orange, because this is not possible. This is bad, which is Damon's past. So therefore, only one message can be sent first. Both situations cannot be true because only one of them can happen first. Either Travis sent the message first or Damon sent the message first. But we know Damon sent the message first, so therefore Travis cannot send it because could not have received it because this whole thing is a way to send something back in Damon's time. This violates causality. So this is important because causality of violations happen because special relativity demands that the reference frames experience all the same laws of physics, including special relativity, including measurement of time. Everything happens as the way it should be according to all inertial reference frame observers. There's no safe way then, therefore, to have the laws of physics and to have faster than light travel. Which means that you can't even win by including gravity in general relativity, because in a small enough space, the core elements of general relativity that make it usable is if you have a small enough space, you can always measure the coordinates of general relativity in terms of special relativity. So in a small enough area, you get special relativity. You can't do special relativity globally in GR, but you can do a small enough area. So you don't win with general relativity, and in fact, you could make your measurements so small that they don't violate the curvature of space-time. Maybe we have these things are little ants going half the speed of light, so it's a really tiny thing. We don't care if it's that they're thousands of miles apart. No, maybe they're a foot apart when they do this thing. So therefore, we can have a curvature, really strong gravity, but yet in a small enough area, it's special relativity. So we don't win. That's the important thing. Special relativity and causality demand no faster than light travel. Tachyons, which are the putative best thing, or is something that would move at the faster than the speed of light. People have talked about them for a long time. So tachyons would be, the first choice. We can make up anything else we want, but anything moving faster than the speed of light would have the same problem. And special relativity is really, really, really well established. It, in fact, is the core of most of our measuring system at this point. So we do have a few caveats, of course, like the indices of refraction. You can actually make materials where the speed of light in the material is very, 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 very slow, and photons pass through it very slowly. And you can make it so that an electron might go faster than the speed of light in the medium that it lives. And it'll create what we'll call this blue light called Cherenkov radiation. It's like something like, say, a neutron or something is going faster than the speed of light in the medium. And you'll see the blue glow in, say, a nuclear reactor pictures, because that blue glow is from neutrons that are going faster than the speed of light in water because of how fast they're coming out of the pile of nuclear material. So we also then have but that doesn't really, but we're talking free space from the previous thing. But even indices of refraction like this, no matter what, we can't use an index of refraction to push us things back in time, because again, we would find causality problems if we did that. We can't do that because now we actually have some other signal that's traveling faster than light, and that's the electron. So an electron can move faster than light in a medium like water. The next one is the Big Bang, because if you go far enough away from us, remember the universe is expanding at about 70 kilometers per second per megaparsec. You get enough megaparsecs between you and some distant galaxy, and the universe is expanding at faster than the speed of light away from you past that point. Now that's interesting, and people say, well, they're rushing away from us. But we didn't push them. And this is only due to the expansion of space itself and not due to anything else. Space itself can expand at faster than the speed of light because it's not a thing, it is space. And so, that's tricky. But we're also looking at the nature of when you expand space, you are expanding at kilometers per second per megaparsec. So you can't actually send a signal back and forth. You can send one signal, say what the distant galaxy looked like a long time ago, and when we get it, we can't send anything back to it because we're looking from the past. Again, special relativity still works here because we're looking at the galaxies in the past. We don't see them as they are now. Quantum entanglement is also a really funny thing. You take two particles, you put them in two separate boxes, you shake them up, you have them interact in some way. They become in an entangled quantum state, and you can separate them. And then when you measure one of them, the other one's measurement will say, maybe you're measuring spin up on a particle, and you open the box and you put two particles together, and then you say let them interact. And as you let them interact, you put them each in their own box without observing them. You just know they're in separate boxes, and you separate the boxes apart. And then when you measure the spin on one, and you know that both of them, either the particles are either spin up or spin down, and one must be spin up and one must be spin down. So therefore, when you open one of the boxes up, that one that you open that's spin up, in entanglement might say that fixes the other one to spin down. And so we find that the way that that's explored, because that was Einstein's spooky action at a distance, and it's also been experimentally verified that there are no hidden variables. So this concept of quantum mechanics entanglement seems to make people think that there's faster than light travel happening, but really it's actually, you'd say that the entire thing, with the space between it and the entire mechanism that did the separating, is the thing that is the quantum experiment. So you actually didn't separate them. Everything that separated them participated in that is part of the entanglement now too. And I know that was really fuzzy. I'm sure I'm going to get flamed for it. But hey, quantum entanglement itself still does not violate causality and still does not yet constitute a faster than light travel. However, the most important thing is it's fun. Faster than light travel smells fun, is fun, and makes for really good science fiction stories. And you're going to get all sorts of really great stuff if you go find it. Some of the stories are good, some of them are bad. But unfortunately for today, even though people really want to do it, and if you go hunt around, you're going to find legitimate scientists and legitimate thinking actually trying to figure out if it's possible to go faster than the speed of light. And the reason for that is that would show a flaw in special relativity or a flaw in general relativity. But so far, as according to normal science rules, and normal science rules are, theories and ideas stand the test of time because they satisfy experiments and nothing else can explain them. So far, every experiment that's been done, no matter how it's been done, has confirmed the truth of special relativity. That doesn't mean it won't be overthrown, but it does mean that right now special relativity wins the day, and it does mean that maybe some smart rabbit will come up with some interesting thing, some woozle compactorator that actually does send the ham throttle faster than the speed of light. But that will involve upsetting 100 years of experiments that verify that faster than light travel cannot be done and that it violates causality. So the only way faster than light travel would be allowed is if it doesn't violate causality. Or if it does, then an experiment might say, well, if you violate causality, you're not violating the causality of our universe. You are in a many worlds interpretation of quantum mechanics, and it's just fine to alter the past of some other universe, which you're not part of. So when you send something back in the past, you are not actually influencing yourself. You're influencing some other universe, and your future goes on normally, but you've sent that message back in the past, and it's gone to some other place. I hope that this has been a lot of fun for you, and we'll see you next time.